The shop in the Students' Union here have a new brand of pre-packed wrap in their meal deal, and these boast that all of the packaging is environmentally friendly and recyclable. But you can see that they're still wrapped in this transparent plastic type material, which doesn't seem very sustainable at first glance. So in order for this to be environmentally friendly, it's got to be very different to our usual plastic.
Oh yeah, I should probably update this intro.
Now, the first sign that it is definitely a different material is how it behaves. So I have here the plastic sleeve from something else, and when you crumple it up, it kind of springs right back. It's almost impossible to crease. But this newer one, well, this crumples almost like paper. Clearly, these don't behave the same way, and they're not going to be the same material. Now, a good rule of thumb is that this one, which doesn't crumple but springs back, is going to be a petroleum-based plastic, probably polyethylene or polypropylene. While this, which will crumple and stay that way, is some kind of biopolymer. That's a plastic-like material, but using biological materials as its starting point. That's not always going to be true, but it's a reasonably reliable way of telling the two apart. And then I thought, hang on, I'm in a chemistry building, we can literally find out what these things are made of. So let's head to the lab.
Anyway, we'll do this next bit with a voiceover because the lab technicians and fume hoods were making a lot of noise. Well, what we have here is an infrared spectrometer. So for the uninitiated, infrared is light that has lower energy than the visible light that we can see with our eyes. It's off to the red side of the electromagnetic spectrum. One reason we can't see it is that infrared doesn't normally have enough energy to start chemical reactions, but it can make molecules vibrate in different ways. So the chemical bonds in molecules will stretch or twist in response to a specific wavelength of infrared light, which we can measure with a spectrometer. And these exact wavelengths are usually characteristic of particular types of bonds and groups in molecules. If we see a broad response around 3,500 wave numbers, it's probably an alcohol. There's a big sharp peak around 1,700 wave numbers, it's likely a carbonyl, and so on. It's the same technique that was recently used by the James Webb Telescope to characterize the atmosphere of an exoplanet. Now, let's go ahead and acquire a background scan so the instrument's calibrated right. Now we have the background, let's add the plastics and acquire a spectrum. This specific version of infrared spectroscopy is known as attenuated total reflectance, or ATR. In ATR, the infrared light bounces inside a diamond crystal. The light never actually goes through the sample, we just place it on top of the crystal and push it down to contact the surface as tightly as possible. This makes the technique incredibly quick and convenient for characterizing materials like this. No mess, let's swap for the second one and record it. Of course, some spectra are incredibly complicated and difficult to analyze by hand, but each spectrum will be characteristic of a certain material. That means we can use a computer to look up existing spectra and try to match it to known samples. Previously, we had to do this by hand in huge books of spectra, but now the computers can flip through all of them in under a second. Now I'll add the polymer database and run the samples through that. And as expected, we have one that is petroleum-based. It's polypropylene. That's one of the most common petroleum polymers in the world, making up about 16% of all plastics. It's a slight variant on the most common one, polyethylene, which is about a third of all plastics. Now, so far, so expected. And if we let the computer identify the other one, it tells us that it's cellophane.
Cellophane is a type of polymeric material based on cellulose. Now, depending on the country you're from or when you grew up, cellophane may mean different things. It's originally the brand name for this specific material, with a trademark held by DuPont for nearly a century. But because cellophane was one of the first transparent plastics ever made and mass-produced for packaging, the name kind of caught on as a generic term for any transparent plastic, even if it's made of petroleum products. But here we're talking very specifically about the biopolymer. Now, to make cellophane, we need to talk about cellulose, which is a polymer formed by connecting glucose molecules together. So basically a long chain of sugar molecules. anyone suddenly remembering their high school level biology, you'll know that cellulose and starch are the same thing, both very common carbohydrates, but they differ in how the glucose molecules connect together and arrange. The result being that starch is edible and digestible by us, but cellulose isn't. And animals that eat cellulose-rich plants digest their food in a slightly different way. So we certainly couldn't eat this cellophane wrap, even if it is a plant-based material. Probably come across cellulose in the form of paper. In fact, running paper through our ATR spectrometer shows it as cellulose or cellophane. The database gets a little bit confused by that one for some reason. To get cellulose, we start with wood pulp and dissolve it in such a way to separate out the cellulose components from tougher materials like lignin. To turn this pulp into cellophane, though, you need to react it with carbon disulfide. This is the sulfur analogue of carbon dioxide, except it's a liquid instead of gas and very, very toxic. It's about as toxic as carbon monoxide, so the vapor can be lethal on the parts per million scale. And it has a long history of harming and killing workers throughout the 20th century through the production of synthetic fibers like rayon, which might be a bit of a problem if you want to claim that this stuff is environmentally friendly. But that said, there are alternative processes to make it, so I can't guarantee that this was made using toxic carbon disulfide or by any other process, so it might have been produced quite cleanly. That's fine, it's just something to consider if you're evaluating how environmentally friendly a product truly is. The other key caveat is that this is not a recyclable material. This is based on cellulose, it's more closely related to paper than it is to polyethylene, but it can't be recycled with paper because it's been reformed with sulfur. Now, one of the ways that we try to recycle plastic materials is to shred it up and melt it back into reusable plastic pellets. But cellophane doesn't actually melt, it burns. And it definitely smells a bit too. It's like burning marshmallow, which makes sense if this is basically polymerized sugar. Now, if this gets into your plastic recycling stream, then you have a problem. It's going to ruin or destroy anything you're trying to recycle. And all that plastic is going to have to go to landfill, or the resulting recycled material will be far, far lower quality. So it's important that this doesn't go into the recycling bin along with other forms of possibly recyclable plastic. As a biopolymer, what it is though is degradable or biodegradable. If you leave this out in damp, oxygenated conditions, it will break down far faster than plastic. Now, not all biopolymers decompose in home composting bins very quickly, but it will certainly break down to nothing and completely harmless byproducts far faster than polyethylene will. So while this plastic might take decades or centuries to decompose to nothing, this one might be gone within a matter of months or even weeks.